I'm Mike Bernhardt for the Exascale Computing Project, once again from SC18. I'm here today with Salman Habib from Argonne National Laboratory. Welcome, Salman. Tell us a little bit about what do you do at Argonne? I know that you do quite a bit, but how would you describe your title?
Well, so right now I'm the group leader for Cosmological Physics and Advanced Computing, which is a group in high-energy physics, but I also have a joint position in Math and Computing Division, and I'm a senior scientist and computational scientist at Argonne.
So, Salman, let's talk a little bit about, you have an application that's kind of in the background here that's running. Wow, it's pretty cool. The viewers won't be able to see it from here in 3D, but tell me what it's about.
Yeah. So that's part of our Exascale Computing Project. And it's a very large simulation of the structure of the evolution of the structure in the universe. And so basically what happens is that the universe starts at pretty much featureless and then over time evolves into these complicated structures, galaxies and so on. And what the next generation observations are going to do is to basically look back into the universe and be able to track billions of objects, billions of galaxies. And in order to understand what's going on, we have to make predictions with very high accuracy of these of this distribution of the galaxies and so forth. So with our latest simulations, we can now actually do that. And what you see in the background is a simulation that actually contains tens of billions of galaxies. But it's so hard to visualize that the visualization itself only captures about 1 million galaxies. And what that visualization shows is basically a flight through of the actual simulation with a simulated observer. So that's what this is about. And this is only the start of our project.
And this is an area, obviously, that's going to benefit tremendously, I would guess, from more powerful when we get into the exascale systems.
Yeah, so this is exactly what our project is about, is basically how do we get to use all the different exascale computing systems at their maximal power. So clearly there will be different types of exascale machines, and so you want a simulation code that can use not just one type of computer, but multiple types of computers and be able to use all of them equally efficiently. So, and at the same time, we have to be able to put in a lot more physics in our simulations. So at the moment, we are doing what you saw in the movie is a gravity-only simulation, but what we are adding right now is gas dynamics and a lot of astrophysical feedback mechanisms. So what is different about our code is, like I said, it runs on all of these different machines, but it'll be able to run problems at scale on these ECP platforms that no one has been able to do until this time.
That's phenomenal. And I understand you just had a new paper published. Can you tell me what that's about?
So one of the big issues with doing gas dynamics is that there are different methods, solvers, if you like, and they all have various strengths and weaknesses. There are methods that are known to be very accurate, but they turn out to be very slow. And there are methods that are fast, but unfortunately can have errors. So one such method, smooth particle hydrodynamics, is a very powerful method. It can do many things, but it also has difficulties resolving certain situations. So what we came up with, this was work led by graduate student Nick Frontieri, who worked with collaborators at Livermore. And we first came up with a new method that extends the smooth particle hydrodynamics method in such a way that it can still do things, still has all the power that it normally has, but it no longer fails on these other issues. So the next task was to take this new method and then put it into our cosmology code, and we have succeeded in doing that, and we have 2 papers coming out of that, and the first one just recently came out, and it is the first cosmological hydrodynamic simulation with a new method. And it shows that all the problems that we were worried about has been taken care of, has very nice results. We've compared with other methods, and we're very happy about that paper.
And is this is it publicly available, the report?
Yes, this paper is publicly available on the archive. Yeah.
How long did it take to put it together?
Well, you know how these things are. It always takes much longer than you think. So it took about, I would say, a year.
I think when people, I'm going to be very general here. People think about cosmology and they look at this kind of study. I don't get it. I mean, I respect it. I see the value in it in many ways, but I can't comprehend it. I can't comprehend the calculations that you have to do to put this together. How long have you been involved in this field of research?
Well, I've been doing cosmology ever since my PhD, and I don't want to say how long that was, but it was a long, long time ago. But I think what has happened in the more recently, starting with, I would say, the mid-'80s and so on, when people first started doing simulations of the universe, is that we have really made a tremendous advance. I mean, it used to be that these are all pencil and paper things, and you could argue about factors of 10. No one was really sure what the answer was. And now we can predict what the universe is doing or had been doing with errors that are of the order of 1%. So this is really quite remarkable. And we have a relatively simple model of how the universe works. And it is also very remarkable that that model happens to be true at such a high level of precision. So two things have conspired to make the universe sort of understandable to human beings, because as I say, our brains are very small and the universe is very large. And I think one of them is the power of computers and the power of human thought. And the second is that the universe just happens to be, on very large scales, something that we can comprehend. It is sufficiently simple. Why that is, no one knows, but that is actually the truth. Yeah.
So 27 years at the DOE National Labs, that's pretty amazing. Is this like the most interesting, most exciting time of your career?
You know, every day I wake up, I feel like in equal measure, it's the most exciting and the most problematic. So I would say nothing has changed. I love working at the labs. So one of the big things that I really like working at the labs is the ability to do team science. So you can have lots of good ideas. You can work them out as individuals. You can also have ideas that you can only work out as teams. And this is, to me, is the best part about working at a DOE lab.
That's awesome. We're sure proud to have you as a part of the Exascale Computing Project. So wish you the best of luck, and we'll make sure that everyone knows how to get access to your paper.
Yeah, thank you very much.
Been talking with Salman Habib from Argonne National Laboratory. For the Exascale Computing Project, I'm Mike Bernhardt.